So in this lesson, we're looking at electrolysis of aqueous solutions. That is the electrolysis of ionic compounds that have been dissolved in water. So let's just track back a bit and let's remind ourselves of the more simple case, which is the electrolysis of molten ionic compounds. So in this example here, potassium chloride, what ions would I have present? Well, as it's just potassium chloride that's molten, then clearly I'm going to have potassium ions, which are positive, and I'm going to have negative chloride ions. That's all I will have. So that when I do electrolysis on molten potassium chloride, then the positive potassium ions will move towards the negative electrode. Whereas the negative chloride ions, well, they will go to the positive electrode. Now, I'm using a couple of new words here, okay? So I'm using this word discharged. All that means is they have the charge removed, okay? So, for example, the chloride ions, when they get to the positive electrode, they'll lose those electrons that give them their negative charge, so they become uncharged atoms again. Now, why do the chloride ions go towards the positive electrode, and why is it that the potassium ions go towards the negative electrode? Well, we'll recall that is because opposite charges attract. In other words, chloride ions are negative and are attracted to the positive electrode because opposite charges attract. Similarly, potassium ions, well, they must be positively charged because they're attracted to the negative electrode. So that's a revision, really, of what we've talked about up to now. And let's just remind ourselves of the reactions that actually take place when those ions arrive at the electrodes. Well, the chloride ions, okay, the Cl negative, they lose electrons to become chlorine atoms. Those chlorine atoms react with one another to form chlorine gas. Whereas the potassium ions lose that positive charge, they become discharged by gaining electrons and forming potassium atoms, which then coat the electrode as solid potassium metal. And we'll remember, won't we, that using oil rig, we can determine which of these reactions is oxidation and which is reduction. Well, if the chloride ions are losing electrons to be discharged, then that is oxidation, oil rig. Oxidation is loss of electrons. Whereas the potassium ions, to lose their positive charge, needs to gain electrons. Okay, so that is reduction. Now we move on to a slightly more complex situation, and that is where I have an aqueous solution of my ionic compound as my electrolyte. Okay, so it's not molten anymore. Instead, I've taken my potassium chloride and rather than heating it to turn it into a liquid, I've instead dissolved it in water to form a solution. So what ions would I have present? Okay, so understandably, I would have my potassium ions and my chloride ions once more. But here's the new bit. I've also got present hydrogen ions and hydroxide ions, which are OH-. Now then, the hydrogen ions and the hydroxide ions come from the breakdown of water. And that's because a small number of water molecules in the solution break down into their ions, hydrogen ion and a hydroxide ion. Okay. You need to know where those ions come from. Okay. So whenever we dissolve anything, we will always have present some hydrogen ions and some hydroxide ions. So, excuse me. Now in my electrolysis, as well as my potassium ion and my chloride ion, I've also got hydrogen ions and hydroxide ions swimming around, okay? So that makes our prediction of our products more tricky. So we need some rules that help us work out what my products will be. So, first of our rules that we need to learn, at the negative electrode, if the metal in my electrolyte is more reactive than hydrogen, then the metal will not form. Instead, hydrogen gas will appear. Whereas if the metal in my electrolyte is less reactive than hydrogen, then solid metal will form at the negative electrode. There will be no hydrogen gas, okay? And really, the overarching principle here is, it is the positive ion from the least reactive element that is discharged. Okay. So, if metal's more reactive than hydrogen, then hydrogen is produced. If a metal's less reactive than hydrogen, then the metal is produced. So let's look at some examples. Okay. In the electrolysis then of aqueous potassium chloride, let's think about what will form at the negative electrode. Well, clearly, I'm just talking about the positive ions, okay? Because we're talking about the negative electrode to which will be attracted the positive ions. But only one of these will be discharged. And we need to use our rules to determine whether it's the potassium ions or the hydrogen ions that are discharged. Again, using that rule, we know it's the least reactive that will be discharged. And we can see on here, potassium is right at the top of the reactivity series, way above hydrogen. So, it is the hydrogen ions that are discharged because hydrogen's less reactive than potassium. That means hydrogen gas will be produced. And we can show that as a half equation. Here we're showing our two hydrogen ions gaining 2 electrons to form hydrogen gas. Okay, they're gaining electrons, so this is an example, of course, of reduction. Let's look at another example. This time, let's suppose we were doing electrolysis on a solution of copper chloride. Okay, there we go, aqueous copper chloride. Well, this time, my positive ions would be, yes, my hydrogen ions, because it's a solution, but also copper ions. Now, this time to work out which will be discharged at the negative electrode, I use the same rule. I look for what are their positions in the reactivity series. Well, here's hydrogen. Copper's below hydrogen. Therefore, copper is less reactive. So using our rule, that means copper ions will be discharged. That means copper metal will be produced. Okay, and once more, we can show that as a half equation. There it is. Again, my aqueous copper ions gaining electrons to form uncharged copper atoms, which will form as a solid. So if we were to add state symbols, that would be aqueous, and then we're forming a solid. Okay, and again, because it's remember, when we talk about oxidation and reduction, we're talking about what's going on with the reactant. My reactant here is the copper ion. It is gaining electrons, so therefore this is reduction. Right, that deals with predicting the products of electrolysis at the negative electrode. Now let's look at what happens at the positive electrode. And again, we've got a rule that we need to learn. And our rule is, well, first of all, we think, does my electrolyte contain ions from a group 7 element? In other words, does it contain halide ions? And the halide ions are chloride, fluoride, bromide, iodide. Those are the ions from the group 7 elements. If it does, then the group 7 element will be produced at the positive electrode. In other words, the chloride ions will be discharged and will produce chlorine. The bromide ions, if they were there, would be discharged and form bromine. Fluoride ions would form fluorine, etc. However, if there is no halide ion in your electrolyte, then instead your product is going to be oxygen. That is the rule. Okay, oxygen will be formed unless halide ions are present, then the halogen element will be produced. Learn that rule. Okay, again, we could look at some examples. Right, so let's suppose we're looking at the electrolysis of, again, let's go with potassium chloride, KCl aqueous. Right, but we're talking about the positive electrodes, so the things we're interested in here are the negative ions. Well, if it's a solution of potassium chloride, it means I've got aqueous chloride ions. And because it's a solution, I know I've got negative hydroxide ions. I need to apply the rule to think, well, what is discharged? The chloride or the hydroxide ions? Well, the rule tells me that if I've got a halide ion, it's that which is discharged. So I've got chloride ions. Those will be discharged and they'll produce chlorine, which, as ever, we can show as a half equation. So this is what's going on. My chloride ions, which are aqueous, turn up at my electrode and they are discharged. They form uncharged chlorine atoms that react with each other and form chlorine gas. Okay, the other products are the electrons that have been removed from the chloride ions. So the removal of electrons, the loss of electrons is oxidation. So this is an example of an oxidation reaction. Let's look at another example. This time, we're looking at the electrolysis of copper sulfate. Right. And I'm telling you that the negative ions that are present are, yes, the hydroxide ions. We know that, don't we, because it's aqueous. But there's these things called sulfate ions. Right, doesn't matter if you've never heard of a sulfate ion before. You can still use the rule. Is there a group 7 ion there? Is there a halide ion? Well, no, there's not. Sulfur and oxygen, neither of those are in group 7. So that means our hydroxide ions will be discharged and oxygen gas will be produced. We'll see bubbles of oxygen forming at the electrode. Now, we can show this as a half equation. Now, the half equation here is a special one. I suggest you learn this off by heart because it is sometimes asked for. And what's going on here is that my hydroxide ions are breaking down and giving off oxygen gas. In addition to the oxygen gas, water is formed, as well as some electrons. So again, my hydroxide ions have been discharged. They've lost electrons. So again, that is an example of oxidation. Right. I suggest you crack on with the contents of the worksheet. Press pause when you need to. Come back and check answers. Maybe have a go at the first one. Come back and check your answer. And then proceed with the others. All the information you need about ion charges will be already on your worksheet or from your notes from this video. Right, so here we're using the rules that we've already gone through to predict the electrolysis products for these aqueous solutions. So we've got copper sulfate, copper chloride, potassium chloride, and sodium sulfate. 4 different electrolytes, and we need to predict what would be produced, first of all, at the positive electrode and at the negative electrode if we did electrolysis on each of these. So copper sulfate. Okay, what would be formed at the positive electrode? Well, at the positive electrode, I need to think, well, which are my negative ions? Sulfate ions and hydroxide ions. Sulfate ion is not a halide ion, therefore I will form oxygen. At the negative electrode, the choice is between hydrogen ions and copper ions. Well, copper's less reactive than hydrogen, therefore I will form copper. Okay, copper chloride solution. This time, my negative ions are hydroxide ions and chloride ions. Aha, chloride ions are halide ions. Therefore, I will form chlorine gas. Again, copper. We've already talked about that. It's less reactive than hydrogen. Therefore, copper will form. Next, potassium chloride. Chloride is a halide ion. Therefore, chlorine will form. This time, though, at the negative electrode, my choices are between a potassium ion and a hydrogen ion. Well, potassium is more reactive than hydrogen. Hydrogen is the less reactive of the two, therefore hydrogen is what is formed. Finally, sodium sulfate. Okay, again, my sulfate ion or my hydroxide ion are my negative ions. Okay, the sulfate ion is not a halide ion, therefore no halogen will form, instead oxygen will form. And at the negative electrode, well, sodium is more reactive than hydrogen. Hydrogen is the least reactive, therefore hydrogen is what will form. Right, using your answers to activity 1, work through the following tasks to write the half equations for each of these reactions that takes place at the electrodes. Then come back and check your answers. So here are our solutions. And of course we can recognise that up here we have oxidation, and of course the second one is reduction. Oxidation, reduction, oxidation, reduction, oxidation, reduction. We can see that at the positive electrode, oxidation occurs, whereas reduction happens at the negative electrode. Now, a really important example of the electrolysis of an aqueous solution occurs with the electrolysis of sodium chloride solution, commonly known as brine. It's just a different word that means sodium chloride solution. So here, well, what ions would be present? Well, I've got sodium chloride, therefore I'm going to have a sodium ion and a chloride ion. But we know because it's a solution, we'll always have hydrogen ions and hydroxide ions also. We know we can use rules to predict the products. So therefore, at the negative electrode, my choice is between the sodium ion and the hydrogen ion. Okay, well, hydrogen is the least reactive, therefore I will form hydrogen gas at the negative electrode. Whereas at the positive electrode, the choice is between the halide ion, chloride, and hydroxide ions. Well, we always know the halide is the thing that is produced, so I'll form chlorine gas. So look at that, I'm forming two gas products. What will be left in solution? Well, I've used up those, I've used up those. So still in solution will be sodium ions and hydroxide ions. Well, we can show that with the formula NaOH, sodium hydroxide. And certainly you could find an important use for each of these if you did a bit of research on the web. I'll give you some uses for these though in a moment. So I'll just quickly skim through this because we've kind of talked about it. If we're electrolyzing a sodium chloride solution, then the chloride ions will lose electrons to form molecules of chlorine gas. They've lost electrons, clearly they've been oxidized. Each chloride ion loses one electron, but we need two chloride ions to make a molecule of Cl2 gas. And there we can show it using a half equation, which we've met before. Now, yes, you might expect sodium to form at the negative electrode, but we know now, don't we, that hydrogen will be formed. And that's because water that makes up the sodium chloride solution contains hydrogen ions, and at the negative electrode, the hydrogen ions are the things that are discharged, using our rule there. And so our hydrogen ions gain electrons, they are reduced. Each hydrogen ion needs to gain one electron. And we need two hydrogen ions to make a molecule of H2. And the half equation, we've met it before, there it is. So we have four types of ions: sodium ions, chloride ions, hydrogen ions, and hydroxide ions in a solution of sodium chloride. The chloride ions form chlorine. The hydrogen ions form hydrogen. We've discussed that already. So what's left? Well, I've already talked about that. We form sodium hydroxide is left behind. Okay, that is an alkali. Strong alkali. So, to your worksheet, delete the incorrect word, then come back and check your answers. So, in the electrolysis of sodium chloride solutions, the negative chloride ions are attracted to the positive electrode. When they arrive there, they lose electrons. That means the chloride ions have been oxidized. Okay. The hydrogen ions are attracted to the negative electrode where they gain an electron to form hydrogen atoms, which then form molecules of hydrogen gas. That means our hydrogen ions have been reduced because they've gained electrons. Now, uses of those products of the electrolysis of sodium chloride solution, the electrolysis of brine. Chlorine, massively important for killing bacteria. Okay, so it's used to treat water. Hydrogen that's made, it's used for so many things, making vegetable spreads, making fertilizer, making explosive, making rocket fuel, you name it. Sodium hydroxide solution that was left behind, well, we use that to make soap, lots of other chemicals, okay? Masses of uses for sodium hydroxide. The electrolysis of sodium chloride has such a wide range of important industrial applications. Finally, press pause, go and have a go at this summary exercise, then come back and check your answers. So the products when an aqueous solution is electrolyzed depend upon the relative reactivity of the elements. Okay, a negative electrode, hydrogen gas is produced if the metal is more reactive than hydrogen. At the positive electrode, oxygen is produced unless the solution contains group 7 ions. This happens because in the aqueous solution, water molecules are broken down to produce hydrogen ions and hydroxide ions.